A quick look at radioactivity and nuclear chemistry. Just a review from your Gen Chem class. Atomic number Z is a number of protons in nucleus. Mass number is a number of protons plus number of neutrons. Of course, it's a whole number. It's the same as atomic number plus number of neutrons. So when you're writing symbol, X element symbol, to the left side above, it will be mass number, and below atomic number. For proton, you'll have notation hydrogen 1, 1. We do not count electrons. Or simply P 1, 1. Atomic number is 1 and Z is 1. There is no neutrons. For neutron, you have number of protons 0, number of neutrons 1. 1, 0, N. 1 for mass number, 0 for charge, for number of protons. For electrons, we would say that number of protons is -1. It's a little bit artificial. It will be charge of nucleus. And of course, mass number is 0. For positron, you'll have the same, just opposite. So it's artificial because when you write +1, for Z it's number of protons, but there is no protons in positron, so it's charge. Alpha particle is simply nucleus of helium. So it has 2 protons and 2 neutrons. In total 4. So these are common particles we have in radioactive decay. So let's look at them. Beta decay. Release of beta particle, which is electron. What happens? You are decreasing number of neutrons by 1 and increasing number of protons by 1. 2 examples. Beta decay of carbon-14, unstable carbon, and beta decay of potassium-40, most common isotope of potassium. All potassium we have on this planet is mildly radioactive. Something to remember when you are scared of radioactive compound. You cannot live without potassium. So what happens? A neutron becomes proton and releases beta particle. But that happens inside nucleus. So it's slightly different. Positron decay. When you have carbon-11 becoming boron-11 and releasing positron. Increase number of neutrons by 1, decreasing number of protons by 1. In both cases, mass number is staying the same because you are removing or electron or positron with mass number of 0. Electron capture decay. Electron from outer orbital is captured, and you have increased number of neutrons and decreased number of protons. Examples are electron capture by argon, by iron 55, and what's important, alternative reaction of potassium making argon. That's actually a source of argon on this planet. And then alpha decay. It's mainly for heavy elements. Polonium releases alpha particle becoming lead. Decrease number of neutrons by 2, decrease number of protons by 2. And the last is spontaneous fission, relatively rare process. When californium falls apart into 2 indium and releases 2 neutrons. Kinetics of radioactive decay. We say that parent isotope releases daughter with rate proportional to number of parent molecules, though this is first order kinetics. As usual, for first order kinetics, we have decay constant or rate constant of decay, which is the same. In radioactivity, lambda is common. And now it's half-life, which is natural log of 2 divided by lambda, or approximately 0.7 divided by lambda. At this time, 1/2 of parent isotopes will decay. This can be source of radioactive dating. Nitrogen, natural nitrogen, reacts with neutron coming from space to become carbon-14, which is unstable isotope. Carbon-14 decays, giving beta particle and gamma particle, which is photon. Now, half-life of carbon-14 is 5,700 years. So looking at concentration of carbon-14 with any object that is solid and cannot exchange carbon with environment, we can say how much time it is dead. For example, for burned wood, this is a very nice way to check. For a large term, you can use uranium-238 dating. The reaction is multi-step process resulting in lead-206. Half-life is 4.5 billion years. So we can calculate how much uranium you have and how much lead-206 you have in your sample. And from there you can figure out how long it took for this sample to exist with no exchange with environment. Radioactive decay from potassium-40, uranium-235, uranium-238, and thorium as a major source of radiogenic heat coming from Earth's interior to the surface. The interior of our planet is hot because of radioactive decay inside. Historically, the main contributor was potassium-40, but around 1 billion years ago, thorium became more important. And at current moment, the main contributor is thorium-232, and close second is uranium-238. Flux of heat from Earth to the surface is not uniform. You can look at map and see that if you're sitting on a continent, you have much less heat coming from inside. Radioactive heat can be used in artificial devices as a source of energy. Object tablet made of plutonium-238 will be red hot because of heat coming from decay, and it's of course crazy radioactive. But if you need to send something in space or put something in very remote location, so this tablet is safely stored, it can be almost permanent source of energy and as a result source of electricity. Radioisotopes are also used in medicine. For example, from isotope of molybdenum that is produced in nuclear reactor, you can make molybdenum 99, and then you can make technetium. Decay of molybdenum gives you technetium with half-life of 66 hours. Technetium itself decays much faster with half-life of 6 hours. So this is quite unstable system, but because of that, it's relatively safe. After several days, nothing of your radioactive substance will be left. So you can do scan of human body or human bones or so on with radioactive isotopes, sometimes revealing details that are impossible to get by other means. Counting the high energy particles can be done by so-called Geiger-Müller Counter. It's a ampulla filled with argon gas and having 2 electrodes. Between each of them there are several hundred volts. When the particle strikes, the current can go between cathode and anode, and you can record number of such strikes. Very simple device, but very effective. Biological effects of radiation. There are several units. Most standard is so-called gray, symbol GI, 100 rads. Radiation, which is radiation absorb dose. It can be related to metric units, joules per gram of material. Also common is Röntgen equivalent for men, REM, REM. Which is close to 1 rad. Q will be coefficient, quality factor. Doses we are getting with normal are coming from cosmic rays on this surface, high elevation, slightly higher dosage. Ground and surrounding, again, depends where you are. Human body emits some radiation from carbon-14 and from potassium. It's natural, cannot be avoided. Average, you have small doses from medical and dental tests, unless you do computer tomography, which will be much higher dosage. Air travel will do something, and then, of course, contamination from human activities, which is relatively small fraction. It's important to understand that effect of alpha radiation is much stronger for a very simple reason. Alpha particle is much larger. On the other hand, alpha particle with alpha 20 is easily absorbed even by air. Now, it's interesting that there are some living creatures, bacterial level, that can survive very high dosage of radiation, essentially can live in a reactor, nuclear reactor. It has unique quality in which it can repair single and double-stranded DNA. It has multiple copies of its genome and rapid DNA repair mechanism. Usually repairs breaks in chromosomes within hours in a relatively simple process. It's very interesting effect and very important for studying and understanding what happens with the biological system under radiation exposure.